Welcome to this lecture series in real analysis. In this lecture, we'll learn the L'Hopital's rule for calculating limits, and let us recall some relevant material. So we'll need to know what is Rolle's theorem. I don't want to recall this in detail, but it just says that if suppose you have a differentiable function, which takes the same value at 2 points, a and b, then somewhere strictly between a and b, its derivative vanishes. So that's that, but we will be also using a generalization of it, which is the Cauchy's mean value theorem, which says what? Which says suppose you start with two continuous functions which are differentiable. Well, they are defined on the closed interval a comma b. We are assuming they are continuous functions, and we are also assuming that they are differentiable in the interior of the interval. Further assume that the derivative of g does not vanish anywhere in the interior. Then this ratio is equal to the ratio of the derivatives, but the key point here in this theorem is that the same c works for both f and g. So there is a c strictly between a and b, such that this ratio is the ratio of the derivatives at the point c. If we just blindly use the Lagrange's mean value theorem, you will obtain a c above and a c below, but those two c's might be different. But with a little bit of trickery, which with the help of Rolle's theorem, in fact, we proved that there is a single c which satisfies this equation. It's a remarkable result. Lagrange's mean value theorem is just a simple consequence of this, where you put g as the identity function so that the denominator becomes b minus a. Okay, all right. So here are some problems for practice. The first one is marked as star, not because it is hard, but it will be helpful in one of the steps. Although I don't intend to give too much details in this lecture, but still. All right. So what is L'Hopital's rule? L'Hopital's rule is useful in many situations. One particular situation is suppose you find yourself with the task of calculating the limit of a function of the ratio of two functions. And you observe that f of x naught is 0 and g of x naught is 0. X naught is the point at which you're calculating the limit. Suppose you find that f of x naught is 0 and g of x naught is 0. Then L'Hopital's rule can help simplify your job, provided some extra hypothesis is satisfied. Then L'Hopital's rule can help make your job much easier. So let's state the formal theorem and at least give some pointers to the proof. I won't be doing too much details. So start with two differentiable functions defined on an open interval I. So I is assumed to be an open interval and x naught is a point in the open interval. Suppose both the functions vanish at that point. Further assume that the derivative of g does not vanish anywhere on a deleted neighborhood of x naught. So this is the point x naught, this entire thing is the interval I. We are assuming that there is some deleted neighborhood of x naught where the derivative of g does not vanish. It may vanish far away from x naught, but in a neighborhood it does not. And assume that this limit exists and is equal to a real number L. So this L is a real number. With that in hand, one can say first that g does not vanish anywhere on some deleted neighborhood of x naught. So we had this assumption on the derivative, but we can say the same about the function itself. More importantly, we can calculate this limit. So the message is, if you can calculate this limit, you can calculate this limit, and those two things are equal. But of course, you need some hypothesis, a very mild hypothesis. If f of x naught and g of x naught are not both 0, or let's say both are non-zero, and we had continuous functions, suppose most of the time, you're assuming that the functions are differentiable, so they are anyway continuous. So if these two things were non-zero, then you already know this limit. So it is interesting only when both of them are 0. If only, let's say, the denominator is non-zero, still you know this answer. So it's interesting only when it is 0 by 0 form. That is how we say it. Anyway, so this is the precise statement, and let's at least give some idea as to how to prove it. So we are interested in this ratio as x is close to x naught. So first, we will write this as this ratio, which is simply because both of these are 0. So doing this is trivial. It's a kind of a underwhelming step. But now by Cauchy's mean value theorem, this is equal to that ratio where what is Cx? Cx is some point strictly between x and x naught. So let me draw a figure. Think of this as the open interval I. Somewhere we have x naught. And suppose we had chosen a point x here. And we considered this ratio. We are saying there is a point Cx somewhere here, somewhere in this region, such that this ratio is actually equal to that ratio. But if x is very close to x naught, Cx is even closer to x naught. And we understand the behavior of this ratio as the argument is very, very close to x naught because this limit is equal to L. So this is close to L. Right? So if x comes closer and closer to x naught, this ratio comes closer and closer to L. And that is essentially this statement. Now, where did we, use all this hypothesis that G prime doesn't vanish anywhere? So for that, first we need to establish that this is the case. Only then we can talk about this ratio. Right? So therefore you need this hypothesis. So how does one follow from this hypothesis? Well, we want to show that G does not vanish anywhere on some deleted neighborhood of x naught. Alright, we are given that G prime doesn't vanish on some deleted neighborhood of x naught. Let's say it is this neighborhood. I don't know how to shade it. Let's say on this deleted neighborhood, G prime doesn't vanish. Now, if G vanished somewhere in this neighborhood, we are claiming that G will also not vanish anywhere on this deleted neighborhood. If G vanished, let's say at this point, G is already vanishing at x naught. G is a differentiable function. So by Rolle's theorem, it will vanish the derivative of G will vanish somewhere here, strictly between the 2 points, and that will contradict 1. So using this, we are able to prove that immediately. And once we have that, this is a meaningful ratio. And once we have this ratio, we played this small trick, applied Cauchy's mean value theorem, and argued that this ratio is close to L if x is close to x naught, and that is essentially what a limit means. So we have established this. I did not write down a proof, but I hope you can. Given all of this, we should be mature enough by now to convert such arguments into formal proofs. All right, so let's see an application, a small example, I mean. So suppose we want to calculate this limit. The numerator, if you just apply, if you just substitute 1 in place of x, will vanish because you'll get 3 minus 2 plus 4 minus 5. So that is 0. And similarly, the denominator is also 0 at x equals to 1. Further, in a neighborhood of 1, G prime does not vanish because what is G prime? So yeah, so fx is the numerator, gx is fx is the numerator, and yeah, I don't want to make a mess. So yeah, I'll just say it. Fx is the numerator and gx is the denominator. So what is G prime x? G prime x is 16x cube minus 2. And G prime x doesn't vanish at 1. So G prime 1 is non-zero. And since G prime x is a polynomial, it is in particular a continuous function. So therefore, if G prime 1 doesn't vanish, G prime doesn't vanish in a neighborhood of 1. Cannot. So the conditions for L'Hopital's rule are met once we can show that the ratio of the derivatives has a limit as x approaches 1. So let's compute this limit, where f is the numerator and g is the denominator. So what is this? This is same as this limit, 9x square minus 4x plus 4 divided by 16x cubed minus 2. Now, this limit is very easy to compute because this is a continuous function which does not vanish at 1. So this limit is just obtained by substituting x equals 1 in the place of x, which is equal to 9 minus 4 plus 4, which is 9 divided by 14. So that's the limit. Very easy. In principle, or in fact, in practicality also, since you know this vanishes at 1 and this vanishes at 1 and both are polynomials, you can factor out this by x minus 1. You can write this as x minus 1 times some other polynomial. Similarly for the denominator, then you cancel out the x minus 1 factor, and then the remaining factors will be very nice to deal with. But that will definitely be more work, more computation. Here L'Hopital's rule is so useful. Alright, so that's a very small example to illustrate the power of it. Later we will put to use L'Hopital's rule towards theoretical purposes, especially in the proof of Taylor's theorem, although whatever application we have in mind, we can also get by using Cauchy's mean value theorem. After all, the proof of L'Hopital's rule relies on Cauchy's mean value theorem. Anyway, so here is the last thing I want to say, that there are other versions of L'Hopital's rule, and I've stated them here. There may be even more versions, I don't know. So take all of them as exercises. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.